Right, so at this point in your learning about limits, then you have learned almost enough techniques to be able to handle most of limits problems, most of standard limit problems out there. So let's take things in a little bit slightly different direction here. So the plan now for the next couple lectures, I am going to investigate a couple previous concepts, a couple old concepts, meaning concepts you have learned prior to being in calculus course. But this time, bringing up those old concepts, but we're actually going to put the limits understanding on top of that so that we can have a better understanding of some of those old concepts that we have learned back in algebra. So in this particular lecture right now, it's going to be a short one because we are going to reinvestigate the whole idea of vertical asymptotes. So allow me to write down the discussion title over here. So we're going to be looking at or reinvestigating what it means by having vertical asymptotes. All right. And so prior to our class, and the reason I'm saying that vertical asymptote is an old concept, and yes, it is true, we have seen this way back in our very early day with learning about algebra. But then, believe me, if we're looking back into any of those courses, back then in those days, when anytime we brought up that topic about vertical asymptote, either instructor or students can only understand vertical asymptote as, so bringing up a graph. A vertical asymptote is we have a vertical line where the graph of the function is getting close to that vertical line, but without crossing it. So graphically, I'm trying to give that explanation right here. And so from the right-hand side, the graph can be also getting close to that vertical line, but as we keep getting closer to that vertical line, the graph will never cross. So if we want to get over to the other side, we have to lift our pencil and jump to the other side and draw a completely different piece. So right here is one good graphical illustration of what it means by having a vertical asymptote. So for whatever function here, f of x, that has a function with a graph like this, then x equals a is a vertical line. And this vertical line in my current graphical illustration, I'm regarding to that as a vertical asymptote. But now, what do I mean by we're trying now to apply our limit concept, our limit understanding into reinvestigating vertical asymptote? So you can see that the graph here, and I did use that term right here, that the graph it's on its own, two pieces, is trying to make its way to get closer. Get closer is the concept we just now recently learned. And so in the way how I see in this current picture that I'm drawing, then as I'm getting closer for this function, f of x, but if I'm attempting to find the limit of the function as x is getting closer to a, but from the left-hand side, then with your experience in estimating limits, from the left-hand side, when x getting close to a, then this function goes to a, or grows to a positive infinity. And then on the other piece, from the right-hand side, the same function. But now if we're investigating the limit of this function as we're letting x coming close to a, but from the right-hand side, and that's what this right-hand side piece, the piece to the right-hand side of that vertical line is doing, then this graph is vertically dropping down and vertically dropping down. So we can, in our limit understanding, we're saying that the limit of f of x as x getting close to a from the right-hand side here is a negative infinity. And so we're starting to get there in terms of formalizing what exactly it means by having a vertical asymptote anytime we're having what I mean is we're getting close to getting that clear understanding of what it means by having a vertical asymptote here. And so let me bring up another picture. we can be having another picture like this, where there is a vertical line, x equals a, and around a, from the left-hand side, the function could be behaving like this, and from the right-hand side, the function could be behaving like this. Okay, so in this way of how I drew my graph here, once again, if we're investigating graphically that from the right-hand side and this function f of x, once again, another picture of f of x right here, a different graph of a different function, but I still named f of x. As we're letting x get close to a from the left-hand side, we've learned from our earlier lecture about how to estimate a limit for a function like this. Then we're looking at having a positive infinity. And from the right-hand side on this function, as we're letting x getting close to a from the right-hand side, then this right-hand side piece also grows to positive infinity. And so generally for this function, since both sides, now neither one of the side limits here go to a finite limit, but in the end they're approaching in the same direction. And so we can also generally regard to this function that as x is getting close to a from both sides, then our function f of x goes to the positive infinity limit. All right. So now at this point, after seeing a couple of examples that I pointed out right here, we are ready to give a precise definition or a precise understanding of what it means by having a vertical asymptote at a vertical line x equals a in the understanding about limits. So here's my definition. So as a definition, this is my shorthand writing for definition. The line x equals a is called a vertical asymptote. So as a new terminology here, allow me to write in red ink. The line x equals a, this line is a vertical line. So now that vertical line is called vertical asymptotes. Of the function f of x. If one of the following cases happen. Or if one of the following cases is true. So you can have a vertical asymptote at x equals a when your function f of x comes to limits when x getting close to a from the left-hand side. When that comes to limit positive infinity, that's one of the cases. Or the same function the limit as x goes to a from the left-hand side goes to negative infinity. That's another case. So we don't need to have both, but as long as we meet one of these requirements, as long as we can find one of these limits, and so far these are the cited limits here. But that's not all. So, or if on the same function, if your function goes to a limit positive infinity when x getting close to a, but from the right-hand side. So another case here, that's also how we can define having a vertical asymptote as x equals a. Or your function f of x is having a limit going to negative infinity as x is getting close to a, but from the right hand side. And then each one of these is one case that I was approaching a from either the left hand side or the right hand side, or from the left hand side or from the right hand side. So the last two cases here, the function f of x has limits as x getting close to a, but generally from both sides, and that limit there goes to positive infinity. That is another case, but this case here we're getting close, we're letting x get close to a from both sides. And the last case here is when your function f of x has limits as x comes close to a, generally from both sides. That gives the limits negative infinity. So anytime that you recognize your function has one of the 6 cases here. So the first 4 cases I wrote on my left board here are the decided limits cases, but they have to have either going to positive infinity or going to negative infinity. Or the other 2 cases when we're looking at limits going as we're letting x getting close to a, but from the right, from both sides, and the limits turns out to be either positive or negative infinity. And these are all the cases that you can say your function is having a vertical asymptote at x equals a. So let's now look at an example or a couple of problems in this example over here. So say find the or determine if given line x equals a vertical asymptotes. Given function f of x. Okay, and so part A of our current example, let's say we have a function f of x being defined as 1 over x minus 1. And at the given with the line, so this is a vertical line, x equals 1. So x equals 1 for sure cannot be plugged into the function because it's going to give an undefined. But what we see here is that what the problem is looking for is asking us to determine whether the given line, so the line here is x equals 1. We want to find out if this line can be a vertical asymptote of that respective function given here. And so we had 6 categories, and as long as this line meets one of the 6 categories, then this line can be regarded as a vertical asymptote of this function. And so first thing we can try, we take the limits of 1 over x minus 1. And this limit, we're going to let x get close to 1, but from the left-hand side. Just try with a sided limit like that. And immediately we can quickly use a table of values to get close to 1 from the left-hand side, and it will give us a negative infinity for this limit. And so, and you can always pause the video and construct your own table of values to get yourself convinced about this answer I've made. But now, as long as we found one of the, so this answer right here we have had falls right into one of the 6 categories for defining our line here, being a vertical asymptote. And so in this case, we're making our final conclusion that so x minus 1 is a vertical asymptote. And so VA is usually being used as a shorthand writing for a vertical asymptote. And so that's how we decide. So, and we don't need to work out all of the 6 different limits there. As long as one of the limits give either a positive or negative infinity, we're good to go. And so we found that one right there. That one is so that's now enough to say that we're having a vertical asymptote at x equals 1. So in another example, in another problem of the same example, let's say our function f of x is being given as 1 over x to the 4th power. And this is at the given value x equals 0. So now I want everybody or anyone viewing this video to see this as a vertical line. And so we need to determine, again, back to the other part, back to the beginning description of the problem, we want to determine whether the function, any given function, has a vertical asymptote at that given line right here. And so back in our case, the given line of a given vertical line is here, x equals 0, and we want to find out if this function, if this given function has a vertical asymptote at x equals 0. So now, once again, we can just simply check. We can check with, you could also start out with getting to that limit point from the left-hand side, but this time I decided to go with the right-hand side. And it's just a choice right there. But this limit will give us a positive infinity. So once again, I don't want to move on too quickly, but I need anyone viewing this video to go ahead and pause the video. Construct a table of values for yourself, just like how we've learned that back in the earlier lectures, and convince yourself that this limit as x getting close to 0 from the right-hand side will produce a positive infinity. And so once you've made your own table and come back to resume this video, then you should be convinced about this answer here is a positive infinity here. And that means, once again, our conclusion here for this particular problem, x equals 0 is a vertical asymptote of f of x.